So, hello everyone again. This is lecture number 3 part 1 of alternating current. In the previous lecture we have started the discussion regarding AC power supplied to a capacitor. We were in the end only. I think we did 2 examples, only one example is left. So, let us complete that example and then we can move forward to AC supply to a series LCR circuit. So, let us start today's discussion. I am Sameer Lavankar. This is lecture number 3 part 1 of alternating current. Let us begin our discussion. So, first of all a course outline for you. Currently we are on the 5th topic, that is AC voltage applied to a capacitor. So, AC introduction is being done, in which we have basically understood what is the difference between a AC source and a DC source, what are the advantages of an AC source over a DC source. Then there were several advantages, such as for long distances it is quite easy and there are less leakages of current or voltages if we need to supply voltage from, let us say, point A to point B, which are at very large distances. Then in the next topic about AC voltage applied to a resistor, we understood basically what happens to the current, or what is the value of the current if, let us suppose, an AC source is being applied. So, let us say V is equal to Vm sin omega t, then we got I is equal to Im sin omega t. So, these all were being explained in the AC voltage applied to a resistor. And the third topic we understood about the phasor diagrams, what is actually phasor diagrams, not so prevalent, not so important for AC voltage applied to a resistor, but very important for AC voltage applied to an inductor or a capacitor. So, we basically understood 3 different concepts in the 2, 4 and 5 chapter topics. The first was, if the value of voltage is V is equal to Vm sin omega t, what is the value of current? Is it lagging behind, it is exactly the same, or it is ahead of the voltage? So, these were the 3 cases we understood regarding resistor, inductor and capacitor. Also we understood about the instantaneous power applied at that particular instant, what is the power depending upon the time taken, and what is the average power over a complete cycle. So, these all were the concepts we basically understood. We also did few examples, we also understood a concept called as RMS current, RMS voltage and so on. So, let us start the discussion which we left in the previous lecture and then move forward with the 6th topic, that is AC voltage applied to a series LCR circuit. Okay. So, these all things are already been explained in the last class. For a capacitor we obtained the value of I is nothing but equal to Vm upon I is equal to Vm upon 1 upon omega c into sin omega t plus pi by 2. What does it mean plus pi by 2? It basically means that current is ahead of voltage by how much amount? By amount of pi by 2 phase. Fine. That thing being said, then we also understood about capacitive reactance. In the previous lecture we also understood about the inductive reactance. Please remember, inductive reactance is equal to omega multiplied by L, where L is the self inductance, and the capacitive reactance is basically equal to 1 upon omega c. So, if the question comes that which is directly proportional to omega, so basically we will say that inductive reactance is directly proportional to omega or frequency, but it is inversely proportional to or capacitive reactance is inversely proportional to omega. Similarly, for inductive reactance it was directly proportional to self inductance, but in the case of capacitor it is inversely proportional. So, basically inductive reactance is directly proportional to the inductance and capacitive reactance is inversely proportional to capacitance. So, these were some of the topics which we should remember for our exams. Next concept, I think, yes. So, basically we understood all these phasor diagrams and how we can say equivalently draw the waveform diagram. That thing being said, next thing was regarding the instantaneous power supplied to the capacitor. So, basically we understood that instantaneous value of the capacitor is nothing but equal to I m Vm by 2 into sin of 2 omega t, right. And similarly average power over one complete cycle we obtained as nothing but equal to 0. Okay. So, these all were the concepts. Then we understood this and this example. That thing being said, let us move on to this next example. Okay. So, the question says that a light bulb, so this is a light bulb being made, and an open coil conductor. What does it mean by open coil conductor? An open coil conductor simply means that only there are windings of wire and there is nothing, so no magnetic component is being inserted inside it. Okay. So, a light bulb and an open coil conductor are connected to an AC source. You can see it is connected to an AC source through a key. What is the use of key? Basically a key is used to close the current or open the circuit or close the circuit. Okay. So, a light bulb and an open coil conductor are connected to an AC source through a key as shown in the figure. the switch is closed and after some time an iron rod is inserted into the interior of the inductor. The switch is closed as in the circuit is complete, and now we are trying to, after some time we are trying to place an iron rod. So, iron rod is basically a conductor. So, we are trying to place this iron rod inserted into the interior of the conductor. So, some sort of like this we are trying to insert this iron rod. Okay. The glow of the light bulb will increase, decrease or is unchanged as the iron rod is inserted. Give your answer with reasons. Okay. So, quite evident. So, basically this is a simple concept of using the definition of inductive reactance. So, in the previous class we understood that inductive reactance is nothing but equal to omega multiplied by L, correct. If you increase if you add an iron rod here, it is quite evident that due to this iron rod the magnetic field in the coil will increase. Okay. So, because of this magnetic field increasing, this L value will increase, correct, omega remaining the same because the frequency is designated or is constant because there is no change in the AC source. Therefore, inductive reactance will change. Okay. So, it is quite evident some sort of analogy to resistor is being changed, right. So, if the resistance of the circuit is increased, that means the amount of light bulb or the intensity of light bulb will decrease, right. So, everything which I just said is written here. So, as the iron rod is inserted, the magnetic field inside the coil magnetizes the iron, increasing the magnetic field inside it. So, magnetic field will get increased. Why? Because an iron rod is inserted, or we can say that a conductor of electricity is inserted. Okay. Due to which the inductance of the coil increases. So, okay. So, inductance has been increased, that means the value of L is increased. Consequently, the inductive reactance of the soil increases. Okay. So, we can say that inductive reactance of the soil is of the coil increases. As a result, a larger fraction of the applied AC voltage appears across the inductor, leaving less voltage across the bulb. Okay. So, what does it mean? It basically means that the amount of voltage across this inductor, so amount of resistance which this resistor holds will get increased, and therefore, the amount of voltage across this bulb will get decreased. Okay. Due to which if the voltage get decreased, so basically the intensity or the glow of the light bulb will decrease. Okay. So, I hope it is clear to you. So, basically if the resistance of some other device gets increased, then that means that the voltage of the device which we require now will get decreased, and if it get decreased, then the intensity will get decreased. Okay. So, that thing being said, let us now start a new concept, very important concept as far as this complete lecture series is considered. So, it is AC voltage applied to a series LCR circuit. As the name suggests, series as in everything which is written after series is connected in a series, not in parallel, and LCR basically means that there is an L, that means there is an inductor, C basically means there is a conductor, and R basically means it is a resistor. Okay. Fine. So, AC voltage applied to a series LCR circuit. So, first of all let us look at the diagram. Okay. So, first of all please remember it is an ideal condition. The ideal condition simply states that any internal resistances in the remaining wires is equal to 0. Okay. So, basically there is a resistor R, there is a capacitor C, and there is a inductor L, inductor of self inductance L. Okay. So, figure shows a series LCR circuit connected to an AC source epsilon. As you can see, a series source epsilon is given to you, and because a VV sign is being formed, that means this is an AC source. Okay. So, figure shows series LCR circuit connected to an AC source epsilon. As usual, we take the voltage of the source to be equal to V, which is equal to Vm sin omega t. Now, if Q is the charge on the capacitor and I is the current at time t, we have from Kirchhoff's loop rule. So, basically everything which is provided by this voltage will be equal to this plus this plus this, correct. So, there will be summation of all of them. So, doing that simple summation, we will get what? We will get that L di by dt, that is due to inductor, plus IR due to resistor, plus Q by C is nothing but equal to the voltage produced by the AC source, correct. So, now let us just try to solve this equation and then we can get our results. Okay. So, we want to determine the instantaneous current I and its phase relationship to the applied alternating voltage V. This problem can be solved by two methods. So, first of all we use the technique of phasors, and in the second method we solve our equation analytically to obtain the time dependence of I. Okay. So, there will be two different methods which I will try to explain to you. First we will do technique of phasors and second we will do it by analytical method. Okay. So, let us start the first methodology in which we are trying to understand the solution of this equation using phasor diagram. Okay. So, from the circuit shown in the figure, we see that the resistor, inductor and capacitor are in series, quite evident, as you can see everything is in series here. Therefore, the AC current in each element is the same at any time, having the same amplitude and phase, quite evident. So, current which is passing through this will also pass through this, will also pass through this, correct. The phase of current may be different from voltage, but the phase of every current which passes through a series device will always be the same. That is why it is saying that the AC current in each element, we are just talking about the elements here. So, the the AC current in each element is the same at any time, having the same amplitude and phase. Okay. So, let that current, we are assuming that I is equal to Im sin omega t plus phi. What is our requirement here? We should know what is this value of Im, and second thing we do not know this value of phi. Our basic agenda or basic principle we right now require is we should know, after final completion of the solution, we should know this value of Im and we should know this value of phi. Let us try to calculate. What is phi here? Phi is basically a phase difference between the voltage across the source and the current in the circuit. Now, let us construct a phasor diagram for the present case, and let capital I be the phasor representing the current in the circuit as given by the above equation. Let VL, VR, VC and capital V represent the voltage across the inductor, resistor, capacitor and the source respectively. Okay. So, that thing being said, I think yes, I have explained. So, this is the diagram basically. Okay. We will try to understand whatever is happening in this diagram. So, basically till now what we know is that we are trying to solve this equation using what we can say, using phasor diagram solution. Now, what is the main requirement here? Basically main requirement is we should know the value of Im, we should know the value of phi. Okay. Basic given assumptions was what? That the amount of voltage which is through a resistor is VR, through a capacitor is Vc, through a inductor is VL. Okay. So, now let us start the solution here. So, we know that VR is parallel to I. Okay. So, this line is already known to us. Why it is already known to us? Because we have already completed single individual solution of all of them. We did for a resistor, we did for a capacitor, we did for an inductor. Okay. So, we know that for VR the phase difference for a resistor is always equal to 0. Therefore, VR is parallel to I, as you can see VR is parallel to I, this thing is known. Next is for an capacitor. We know for a capacitor I is front, I is ahead, Vc is behind. That what does it mean? It basically means that Vc is pi by 2 behind I. So, we will just go in this sequence here, because we are trying to do it anti-clockwise sense. If you are trying to do it anti-clockwise sense, that basically means that Vc will be drawn at some clockwise pi by 2 phase difference. Okay. Therefore, this will be the direction of Vc, and then VL is pi by 2 ahead of I, because this also we have already concluded. So, therefore, we will just go 90 degree here and we can draw value of VL. Okay. Fine. So, this is also okay. So, this thing is known now. Okay. Next thing is VL, VR, Vc and I are shown in figure A. As you can see, it is shown in figure A with appropriate phase relations. Okay. So, now let us try to understand more about this. Okay. So, let us first of all calculate the length of this phasor or length of these vectors. Okay. So, let me write or what we can say them to be equal to amplitude of capital VR, basically voltage across resistor, capital Vc and capital VL. Okay. R. Okay. So, basically first of all let us calculate the value for, so it is V R M, what will be equal to, this will be equal to Im into capital R, quite evident side directly I into R, correct. What will be for VCM? VCM will be, so we have already defined two different definitions, one was XL and one was XC. So, I will directly use here. So, basically VCM will be nothing but again same current passing, but this time passing with a XC, and this VLM will be nothing but equal to IM into XL. Okay. So, I hope these three length is easy to retain. Next thing is, now let us try to use Kirchhoff's loop rule directly. So, in the circuit given, these voltages will be equal to nothing but the voltage which is applied by this AC source. Therefore, what we can write? We can directly write that VL plus VR plus VC is nothing but equal to V. Okay. So, therefore, finally, for complete voltages now, so please remember these are small values or small letters. Now, I am writing the equation, same equation in terms of phase relation for actual values of VR, VC and VL. Okay. So, therefore, finally, what we can write as per these phase relations. So, this VRM, VCM and VLM are given to you in this diagram here. So, these were the lengths. Okay. Please remember these were the lengths which I was trying to explain to you. So, it is VRM, then this is your VM, this is your VCM and this is your VLM. Okay. Fine. So, now next thing is, for the phase relation we can give directly that capital VL plus capital VR, simple equation. We are just trying to equate that the total voltage being supplied is nothing but retained by three different quantities. One was VL, the next is VR, next is VC. Okay. Fine. So, now after this thing is being done, we can say that, please understand this correctly, VC and VL are always on the same line. If they are on the same line, even if you try to change it, always the value of VC will be 90 degree behind and the value of VL will be 90 degree ahead. So, it always comes in a straight line only. It depends only upon the value of time at which we are trying to calculate, but always it is coming out to be in straight line only. So, to understand it more clearly, what we can write? We can just change this equation into a single phasor. So, we can basically do VC plus VL. Actual value in actual magnitude sense, this value will be equal to VC minus VL, but for now what we can say is that we are trying to add, basically we are trying to add VC plus VL, correct. This VC plus VL can be added upon as a vector in terms of having a magnitude which is equal to VC minus VL. Okay. So, basically VCM minus VL, because we are obtaining this length as nothing but equal to VCM and VLM. Okay. I hope it is clear to you why we are doing this. We are basically doing this because always VC and VL are always lying on the same line. Okay. So, that thing being said, now what we can do is basically, so see to this diagram clearly. So, here what is actually happening? VC plus VL we denoted like this, correct. So, this is just the phasor diagram, but actually magnitude wise its value is nothing but VCM minus VLM. I hope it is clear to you, right. So, now if you see clearly, this is having value which is equal to VCM minus VLM, and this is having a value which is equal to VRM. Okay. Everything is small, please remember everything is small. The length of the phasor is written in small letters, and if you are trying to obtain complete value, we are trying to denote it by capital letters. Okay. Fine. So, this is VRM, this is VC minus VLM. We know that this is at 90 degrees. We are trying to calculate the complete value. What will be this complete value? This value will be nothing but equal to this diagram, correct. Now, using simple vector addition, we know that this value can be calculated by using the triangle law of vector addition or parallelogram law of vector addition, and therefore, we can get that this small Vm, or basically let me write like this, using vector addition we can get that Vm square is nothing but equal to Vrm square. Please remember everything is small letters, plus Vcm minus Vlm whole square. Okay. So, this is the final relation which we obtain in terms of vector addition. Okay. So, let me stop it here. After this we will just try to derive, we will just input all the results which we just derived in the last slide, and then we can finally obtain a new quantity which is called as capital Z. Okay. So, let me stop it here. I will continue this discussion in the next class. So, thank you so much.